Hello everyone, my name is Jincao Feng. I'm a PhD candidate at the East China Normal University of China. Today, I'm going to introduce our work, an automated and formal approach to requirement modeling and analysis in aircraft control domain. Nowadays, in safety critical domain, they are looking forward to using formal methods to improve quality of the product or simply following the standard. However, they know about the formal methods, but don't know how to apply formal methods to their project. And for software engineering, they are struggle with math notations when using formal methods to their project. It is said that applying formal methods to requirement modeling and analysis in the industry remains a challenge. The first reason is lacking dedicated notations for requirement modeling. The specific domain needs their own approach to applying the formal methods to verify their property. The second reason is that in different domains, they are lacking systematic approaches for requirement modeling and validation and verification approach. The last reason is that some approach lacks the automation tool support their approaches. To tackle this problem, we present a lightweight requirement modeling language that supports the aerospace and aviation domain features. And we also propose a systematic engineering approach FREPA to the formal requirement modeling and validate and verification. Meanwhile, we develop a tool AeroReq that supports the automation of the FREPA. Our approach is made up of two parts. The first part is to model the requirement. The engineers first manually document their requirement and construct their specification and properties with the help of our template. After that, the models can be generated automatically. And then we have 4 validate and verification ways to check the specification whether satisfy their expect. They call the diagram-based review and the requirements simulation and statistical estimation and test case generation. We summarize the features of the embedded control software in aircraft control domain. The first feature is model-based. The control software is a model transition system which always runs in some mode to perform corresponding functions. The system can transit to another mode if the transition condition is triggered. The second feature is computation-oriented. The control software usually focuses on decision and mathematics computations. The third feature is period-driven. The control software performs functions under the restriction of given periods. For example, in the third mode, the satellite has to check the value of the outside temperature every 5 seconds. Our model structure is like that. The model always runs in some mode, and every moment the system stays in one mode and runs its own task, which is called control flow. The control flow is a set of state-style statements without the loop. The control flow calls other modules to run the detailed functions. The mode transition occurs when the condition is satisfied. All the variables used in the model that are defined in the date dictionary. And this is our model structure. Next, let's talk about the input of our approach. We provide a Microsoft Word template to help construct the specification, which means the engineering simply needs to fill in the blanks of the template to construct the specification, and this specification is the input of our approach. The output of our approach is that the requirement-based variables diagrams and the requirement simulation report and the requirement estimation report and the requirement-based MCDC test case. Next, we will use a running example to show how to use our approach. We use a module calculate angle and a mood, slowed mood, as our running example. The first stage is the specification construction. The original requirement is that the system should calculate the angle, and then they just fill in their original requirement into our module template. They use our language syntax to describe their detailed function. Like the module specification, the module specification is also the same. The engineering just fill their detailed contents into our mode template, and then they can construct the specification. Once they finish the field in the template, they get the specification. Once we get the formal specification, we have 4 technologies approach to verify the specification. The first is the diagram-based requirement review, and then is the requirement simulation and statistical estimation and automated test case generation. Diagram-based requirements review means that generate variables diagrams like variable dependency diagrams and state transition diagram, and then the experts review the diagram and validation the requirement whether satisfy their expect. For example, we can generate the mode transition diagram on the left side. The people can check the system whether transmit the slow mode to the normal mode. And we also can generate the variable dependency diagram on the right side. The people can check the A imply B and the B imply C and the C imply whether the A on the other things. Actually, in this stage, we suppose the mutually exclusive check for the state transition system. For example, when the system stays in slow mode, if the N2P equals to 01, the slow mode can transmit from the slow mode to the beyond slow mode and the normal mode at the same time. Is the error. Based on our diagram, the experts can find some errors like that. Simulation is often used for the system design phase. That is because in many cases, requirements are not precise for automatic simulation. But the FREPA formula defines the requirements such that automatic simulation becomes possible. In our requirement simulation, we get the value from the environment model and calculate the value by model. And we simulate the model period driven. And then we store every period the results of the simulation. We detected 2 errors based on the simulation. The figure has a breakpoint because of the mode transition condition failed. The simulation system don't know which mode is the next mode to stay. So they show a breakpoint in this figure, but we can see in requirement simulation, if 2 results are not the same, there might exist error. And we think the requirement simulation is very useful to find errors in early paths. That means when requirement engineering writes their requirement, they can simulate the requirement to find the errors which doesn't satisfy their intent. Next is statistical estimation. Traditional model checking can't directly adopt because the aircraft execution is also affected by the random environmental factors. So we use a lightweight version of model checking. We use the statistical methodology to estimate the probability of a model satisfying the given property. We use a property example to explain our methods. For example, if the system should satisfy the property like that, the system starts from the mode M2 and then it will finally transit to the mode M5 or mode M6 or mode M8 and stay forever in one of these three modules. To check this property, we first translate it into the LTL property, and then our approach can verify the system whether satisfy this property. In our methods, this property is never satisfied in any execution path, so this property is never satisfied. Next, our approach supports the test case, the automated generation. The requirement-based test case can be used to achieve the complex coverage of each requirement and can be used to detect it of an intended data flow relationship between the inputs and the outputs, and also can find the dead code and the deactivated code. But however, the requirement-based test case is often written by the human. It's really labor cost job. Our approach supports the automated test case generation from the requirement. In general, executing the test case under the MCDC coverage, it can detect errors in both source codes and the requirements. The automated generation of such test case from requirements also calculates the testing on the implementation stage. The approach has applied to 9 engineering control systems for formal validate and verification. Based on the contract with our industry partners, we only have the chance to use the FREPA from scratch on one of the systems each as a demonstration. And other systems that applied FREPA to are completed by our industrial partners due to the privacy regulation. So we thus introduce the evaluation results on these two demonstration systems. The formal specification of the aviation system is a 128-page Word document with 10 system modules, 139 modules, and 1,200 variables, while the specification of the aerospace system is a 145-page Word document with 14 system modules, 14 two modules, and 420 variables. FREPA has been used in industrial projects to help detect requirement problems in the test adequate requirement. For example, through the diagram-based requirements review, we dedicate 26 errors in requirement. And through the requirement simulation, we detected 2 errors, and through the statistical estimation, we found 3 property can't satisfy, and it also the requirement errors. Although the diagram-based requirements review found more errors, but it found the easily errors. The deep level errors is found by the requirement simulation and statistical estimation. The MCDC test case generation now is only used for support testing engineering. It's really convenient for them to support them to write their test case. They can based on our advice to write their test case. Formal methods can be significantly helpful if they are properly implemented, but the engineers only want to focus on domain knowledge. They don't have much time to learn formal methods, and meanwhile, the engineers only want to use formal methods rather than learn it. So we don't have waste time to teach engineers to learn formal methods. Otherwise, we should develop a systematic approach to apply the formal methods. That is our license. We learn that do not ask the engineering to learn formal notations or prove knowledge. And we also learn that do not make aggressive changes to the engineering custom to modeling and validate and verification. And never underestimate the importance of the tool support, because the one-click tool is very important for engineering. And in this paper, we present a formal engineering approach, FREPA, to the formal requirements modeling and validate and verification in the aerospace and aviation control domains. We also have developed a supportive tool, AeroReq for FREPA, provides users with a requirement specification construction and validate and verification environment. So far, the FREPA has been applied to real aerospace and aviation control systems from our industry partners. And we also report the experience and license when using our approach in the industry. This is our presentation. Thanks for listening.